It starts with a simple glance up at the night sky, that quiet glowing face we've always known as the moon, steady, peaceful, and constant. It's been up there for billions of years, circling our planet like a silent guardian. But what if one day that calm was shattered by something completely unexpected? Not an asteroid heading for Earth, but one barreling straight toward the moon. Imagine a colossal asteroid, a frozen rocky mountain drifting through the void, slamming into the moon at thousands of kilometers per hour. No warning, no defense, just a violent, unstoppable crash. It's the kind of impact that could leave the moon scarred forever and send shockwaves of chaos down to Earth. We always think about asteroids as threats to our planet, but what happens when they strike something just one step away? This is the story of what could unfold if the moon took the hit for us, and why that might not be the lucky break we think it is. Now picture the moment it happens. No sound in space, but from Earth, you'd see it. A blinding flash erupting on the moon's surface, bright enough to be visible even in the daylight. An asteroid, perhaps several kilometers across, crashes into the lunar crust with unimaginable force. In an instant, the quiet moon becomes the site of a cosmic-level collision. The blast unleashes more energy than every nuclear bomb on Earth combined, and then some. The moon's surface, already cratered and ancient, would be violently transformed. A new massive impact basin, possibly hundreds of kilometers wide, would be carved out in seconds. Superheated rock and vaporized dust, what scientists call ejecta, would shoot outward in every direction. Some of this material would escape the moon's weak gravity entirely, flung into space at speeds of several kilometers per second. The landscape would ripple with seismic shockwaves, likely fracturing deep beneath the surface and permanently altering the moon's internal structure. And remember, the moon doesn't have an atmosphere to slow anything down. Every bit of debris from this impact is raw, fast, and deadly. Towering plumes of dust would rise and fall in total silence, leaving behind a brutal new scar for Earth to see, a reminder of just how suddenly everything can change in the cosmos. But the real problem, what happens next, when all that material starts moving through space? Because not all of it is going to stay up there. Some of it is coming straight back to us. In the hours and days that follow the impact, Earth would begin to experience the real consequences. At first, the signs might seem beautiful, an extraordinary meteor shower lighting up the sky. But this time, those glowing streaks of light wouldn't be harmless. They would be the first wave of lunar debris racing through space and slamming into our atmosphere. The initial wave would mostly be smaller fragments, bits of vaporized lunar rock and dust, no bigger than pebbles. These would create a dazzling but dangerous light show, as countless particles burn up high in the upper atmosphere. Entire skies could glow for hours at a time, even during daylight. But this is only the beginning. Mixed in with the dust storm are much larger, heavier chunks, everything from rock fragments the size of baseballs to debris as large as small houses, and they would not all burn up. Earth's atmosphere can usually break apart smaller meteoroids, but bigger pieces, those could survive the fall. Hundreds, possibly thousands of meteorites would crash across continents and oceans. Most would not be big enough to cause mass extinction, but enough of them could cause serious destruction. Imagine random impacts flattening homes, sparking fires, or pummeling highways and farmlands. A single lunar boulder crashing into the ocean could trigger dangerous waves, or even regional tsunamis. Even beyond Earth's surface, our orbiting satellites would be at risk. The moon's debris cloud would be filled with tiny but fast-moving particles, fast enough to rip through metal. Communication networks, GPS systems, weather tracking, and surveillance infrastructure could all be knocked out. And since this rain of particles would continue for days or even weeks, the damage to satellites could be widespread and ongoing. The Earth wouldn't be hit all at once. This fallout would arrive in unpredictable bursts, creating fear and uncertainty across the globe. And the worst part? No one would know exactly where the biggest pieces might fall next. The impact that began in total silence on the moon would become a loud, chaotic, and potentially deadly crisis back on Earth. With Earth enduring the fallout, the long-term questions would begin to take shape. The moon itself, while still hanging in the sky, would no longer be the familiar, stable companion we once knew. Even though the moon is massive, far heavier than any asteroid that might hit it, an impact of this scale could still alter its behavior in subtle but serious ways. The odds of the moon being knocked out of orbit completely are extremely slim. Its mass is so great that even a giant asteroid, something the size of the dwarf planet Ceres, would barely budge its path. But not all changes would be dramatic. A high-energy impact could slightly shift the moon's axial rotation, or nudge its orbit just enough to disrupt the delicate gravitational balance it shares with Earth. These small adjustments might not be visible at first, but their long-term effects could be significant. Our tides are governed almost entirely by the moon's gravitational pull. If the moon were to lose a large portion of its mass, or change its position, even slightly, Earth's ocean tides could shift in unpredictable ways. Lower tidal ranges would hurt coastal ecosystems that depend on the rise and fall of water. Shorelines, wetlands, and estuaries, places where life has evolved over millions of years, would struggle to adapt. Sea creatures that rely on the moon's pull to breed, feed, or migrate could begin to vanish. And then there's Earth's tilt. The moon acts as a kind of cosmic stabilizer, helping to keep our axial tilt in check. Without it, or if the moon were to become much smaller or lighter, Earth could start to wobble. This wobble, over tens of thousands of years, would swing our planet's tilt from nearly 0 degrees to as much as 45 degrees or more. That might not sound extreme, but such a shift would totally change global climates. Regions that once had moderate seasons could face brutal winters or endless summers. Some areas might turn into deserts, while others would freeze year-round. Agriculture, one of the foundations of human civilization, could become almost impossible in certain zones. And over centuries, entire populations would be forced to migrate as Earth's climate reshaped itself in unexpected and chaotic ways. So while the immediate threat of the impact is terrifying, it's the slow unraveling of our planet's balance that could prove even more dangerous. The moon doesn't just light up our nights, it keeps Earth steady. Without that, the world we know could slowly start to drift into one we no longer recognize. As the years stretch beyond the initial chaos, the true scale of this lunar catastrophe would slowly start to reveal itself. While the bulk of the lunar debris might fall to Earth over days or weeks, the smaller particles, the fine moon dust blasted into space, could remain suspended in Earth's upper atmosphere for years. This high-altitude haze would scatter sunlight, possibly dimming the skies and dropping global temperatures in a phenomenon similar to what happens after major volcanic eruptions. This impact winter might not be as severe as one caused by a direct hit on Earth, but even a mild, persistent cooling could disrupt weather patterns and shorten growing seasons. Crops in some regions could fail, other areas might face unpredictable droughts or flooding. A few degrees of global temperature change is all it takes to shift ecosystems, forcing entire food webs to adapt or collapse. Farmers, already reeling from lunar debris, damage, and satellite disruptions, would now have to contend with a climate gone strange. Meanwhile, Earth's night sky would look unfamiliar, even haunting. A giant new crater would scar the moon's surface, visible even to amateur astronomers with backyard telescopes. If enough ejecta escaped the moon's gravity and got caught in Earth orbit, we could see something no one has ever witnessed, a faint ring system around our planet. Like a dusty halo, this ring would shimmer faintly in the darkness, changing how our nights looked and felt. It might even increase nighttime brightness temporarily, especially in areas already lit by city glow. But these rings wouldn't last forever. Over time, gravity and atmospheric drag would pull that material back down to Earth, causing sporadic meteor showers that could last for decades, maybe even centuries. For future generations, streaks of moon dust lighting up the sky could become a common sight, a recurring reminder of the day everything changed. And what if the impact had been even worse? Say if a massive section of the moon had broken off. The consequences wouldn't just be visual or climatic. Many nocturnal animals, tuned to the moon's light for hunting, navigation, and breeding, would lose a key environmental cue. Species could vanish simply because their world went dark. For humans, the psychological effect of a mangled or missing moon could be profound. After all, it has guided our myths, our calendars, even our sense of time and rhythm for tens of thousands of years. So even if Earth survives the worst of the physical damage, the moon's transformation would mark the beginning of a different kind of era, one shaped not just by altered tides or dimmed sunlight, but by the long shadows of a sky we no longer recognize. The moon would no longer be a silent guardian. It would be a monument to what could happen when cosmic forces collide in the wrong place at the wrong time. As the chaos begins to settle, Earth enters an unfamiliar chapter, one where daily life is shaped by an event no one alive has ever experienced. The dust storms clear, the debris showers lessen, and the skies begin to stabilize, but everything beneath them has changed. For billions of people, the priorities would shift quickly from awe to survival. With damaged infrastructure, collapsed food supply chains, and unreliable communication systems, countries would be forced to rebuild under new conditions. Emergency efforts would focus on stabilizing cities hit by falling debris, restoring power grids damaged by satellite outages, and relocating coastal communities grappling with altered tides. Agricultural zones may have to shift entirely, especially if the impact winter had any lasting effects on temperature and rainfall. In some regions, crop yields might plummet for several growing seasons, forcing mass migration and sparking political unrest. Nations would compete for fertile land, stable climates, and fresh water, all while navigating a disrupted global economy. Scientists and engineers would be racing to understand the moon's altered behavior. Even minor changes in its orbit or spin could have knock-on effects we don't yet fully understand. Predicting tides, tracking long-term climate patterns, and maintaining global navigation systems would become more difficult. For researchers, it would be an unprecedented opportunity to study planetary scale change in real time. For everyone else, it would mean adapting quickly or suffering the consequences. But the psychological aftermath might be even deeper. The familiar night sky, now permanently changed, would become a symbol of vulnerability. For millennia, humans have looked to the moon as a constant. Its phases guided ancient calendars, inspired entire mythologies, and acted as a silent witness to our history. Now that symbol would be cracked, possibly half-lit, maybe even orbiting a few degrees differently, always reminding us of just how close we came to something far worse. Culturally, this could spark a shift in human thinking. People might begin to take cosmic threats more seriously. Asteroid detection programs could receive major boosts. Governments might invest more heavily in space infrastructure, not just for exploration, but for planetary defense. Lunar colonies or off-Earth observatories could go from science fiction to global priorities. And the public, they'd likely become more attuned to the idea that Earth's place in the solar system is fragile, and that survival might require thinking far beyond our atmosphere. So even if life eventually returns to something like normal, it would never be that normal again. This kind of event wouldn't just reshape land or sky. It would change how we think, plan, and prepare. The moon's scar would become a warning. The solar system does not care about our schedules or civilizations. Its violence is ancient, random, and inevitable, and the next target might not be so distant. When the dust finally settles, literally and figuratively, the world would be left forever altered, not just by the damage, but by the realization of how closely we are tied to the moon. The final stage of this disaster would not be a dramatic explosion or a city-leveling impact, but a slow, sobering shift in human understanding. The moon was never just a light in the sky. It was, and still is, our stabilizer, our timekeeper, our shield. The crater now carved into it, or the pieces that may remain if it fractured badly, would become symbols of vulnerability on a cosmic scale. In this new era, Earth's rhythms could feel off. With altered tides, disrupted seasons, and unfamiliar skies, daily life would carry an eerie sense of imbalance. Generations raised with the full moon would now grow up under a dimmer, maybe broken celestial body. Lunar eclipses would no longer look the same. Entire cultures that built mythologies around the moon might have to reimagine those stories. Our calendars, once synchronized with the lunar cycles, could become increasingly detached from what remains of that rhythm. And if the moon had been shattered, beyond repair, if it became a field of debris instead of a single body, the consequences would stretch far into the future. Earth's orbit could accumulate dangerous clutter, making space exploration and satellite deployment more hazardous. For astronauts and space agencies, just getting into orbit could become riskier than ever. Nighttime would grow darker, colder, and emptier, especially in regions that once relied on moonlight for navigation, wildlife movement, and even agriculture. In a quiet but profound way, the world would become lonelier. But perhaps the greatest shift would be in how we view our place in the universe. A giant asteroid hitting the moon instead of Earth might at first seem like a lucky break, but in truth, it would show just how thin the line between safety and catastrophe really is. Earth didn't dodge a bullet, it just watched that bullet hit something it loves. This kind of event would change education, culture, politics, and science all at once. More people would push for asteroid defense systems. Funding for space weather forecasting and cosmic threat detection would explode. The idea of lunar colonies could transform from a scientific dream into a survival strategy. and many would start asking the bigger questions about existence, randomness, and how to plan for threats that come from far beyond our atmosphere. In the end, a giant asteroid hitting the moon would not be a problem we could simply clean up and move on from. It would be a defining moment in Earth's history, a cosmic lesson in fragility, a planetary reminder that, in the vast, unpredictable arena of space, we are not spectators, we are participants. And as long as we look up at the sky and see that altered moon, we'll be reminded that the universe is still writing its story. The only question is whether we're ready to read the next chapter. Just picture it. Hundreds of millions of tons of concrete, steel, and water working together every single second to hold back one of the most powerful rivers on Earth. The Yangtze River has carved its way through the heart of China for millions of years, and it's been both a source of life and destruction. But since the early 2000s, it's been controlled by the massive wall of the Three Gorges Dam, the largest hydroelectric power plant ever built. It stretches for over 2,300 meters across and stands 185 meters tall, almost the height of a 60-story skyscraper. Behind it, a reservoir stretching over 600 kilometers long and holding back more than 39 billion cubic meters of water. That's over 5 trillion gallons. Now this thing is not just big, it's a modern marvel. The Three Gorges Dam wasn't just built for show, it was built with two major goals in mind: stop the Yangtze's constant flooding and produce a huge amount of clean energy, and in many ways it's done both. When the last main turbine came online in the year 2012, the dam reached its full capacity in Altio, 22,500 megawatts, which is enough to power tens of millions of homes. In the year 2020, after an especially intense monsoon season, it hit a world record, generating over 111 terawatt hours of electricity in just 1 year. That broke the record set by Brazil's Itaipu Dam. But here's the thing about it. While it was built to protect and power, the dam now stands as a massive potential threat. The bigger something is, the harder it hits when it falls. If the Three Gorges Dam were to collapse, even partially, the effects wouldn't just be felt in the areas right below it. The disaster would reach across an entire region and ripple out through the entire world. Hundreds of millions of people live and work in cities scattered all along the Yangtze River. These include places like Yichang, right below the dam, and larger cities like Wuhan and Nanjing, farther downriver. These places are not just home to millions. They're packed with infrastructure, agriculture, factories, and key shipping routes. So now comes the big question: how could something so massive and so carefully engineered actually fail? What would it take? Let's start with the most basic problem: gravity and water pressure. That massive wall of water behind the dam is always pushing forward. The structure is built to handle that, but just barely. Like every major dam in the Three Gorges is constantly under stress. Over time, even small movements in the concrete or shifts in the foundation can start to cause problems. And the Yangtze River itself adds to the danger. It's one of the muddiest rivers in the world, and that matters. Every year, around 40 million tons of sediment move downstream. But with the dam in the way, a lot of that silt ends up piling up behind it. Over time, that buildup puts even more pressure on the base of the dam, making the water harder to manage and the structure more vulnerable. Now here's where things get more complicated. The dam sits on a fault line, not a super active one like in California or Japan, but active enough that earthquakes do happen. And scientists have been warning for years about something called reservoir-induced seismicity. Basically, all that water pressing down on the earth can trigger quakes on its own. There's another problem too: landslides. When the water level in the reservoir rises, it loosens the soil around the edges. Since the reservoir was filled, there have now been dozens of major landslides, some so powerful they've caused waves inside the reservoir itself. In one case, tens of thousands of cubic meters of earth and rock came crashing into the water in seconds. Imagine what that could do if the landslide happened right near the dam wall. Even though Chinese officials monitor the dam closely and carry out maintenance and inspections, some experts have pointed out that the original construction may not have been perfect. One hydrologist, Wang Weilo, raised red flags about how the design, construction, and inspection were all handled by the same group. He warned that cracks, rushed schedules, and poor quality materials could come back to haunt the structure down the road. So now we're left with this picture: an aging mega dam holding back one of the largest reservoirs on Earth, sitting in a place prone to earthquakes, dealing with increasing sediment buildup, surrounded by unstable slopes, and facing stronger and more unpredictable storms every year. It hasn't failed yet. But if something went wrong, even one thing, it could be the beginning of a chain reaction, and once that chain starts, there may be no way to stop it. Next, we're going to break down exactly how that failure might unfold. For Dinaos, the conditions that would line up, the timeline of collapse, and what cities would be hit first. It's not just about whether it could happen, no what. It's about how fast, how far, and how horrifying it really could be. It's easy to look at the Three Gorges Dam and just see strength. After all, we're talking about a wall of concrete that's over 2,300 meters long and about 185 meters high. But behind all that concrete is a system that's constantly under stress, physical, environmental, and human. It's a complicated machine built into one of the most unpredictable rivers on Earth. And the truth is, there's a long list of ways things could start to unravel. Let's start with one of the biggest concerns: seismic activity. The dam is built in a region of China that sits on several fault lines. Normally we think of earthquakes as something that just happens out of nowhere, but in this case, the weight of the reservoir itself, billions of tons of water pressing down on the Earth, can trigger what's called reservoir-induced seismicity. That means earthquakes that wouldn't normally happen might occur just because of the stress the water puts on the crust beneath it. Some scientists believe that dozens of small tremors recorded in the region since the reservoir was filled are likely linked to this exact phenomenon. A small quake might be manageable, but a big one, even just in the wrong spot, could push the structure past its limits. There's also the issue of landslides. Ever since the water level rose behind the dam, the steep terrain along the reservoir has been eroding. That's not just theory, there have been real events already. In May of 2009, huge chunks of land slid into the water at Wuxia Gorge, sending shock waves across the surface. In the first few months of 2010 alone, nearly 100 major landslides were reported in the reservoir zone. That might not sound like a direct threat to the dam, but the sediment and debris from those landslides flow toward the dam, slowly clogging the reservoir. That raises water levels, increases pressure on the structure, and decreases the amount of water it can safely hold during floods. Over time, this puts the entire system into a tighter and tighter corner. Now let's talk sediment. The Zhou Yangtze River has always carried a massive load of silt and mud. Before the dam was built, much of that sediment flowed downstream naturally, keeping the river's ecosystem in balance and reinforcing the riverbanks all the way to the coast. But now, most of that sediment settles in the reservoir. In fact, estimates suggest that about 40 million tons of sediment pour into the dam each year. With slower water flow above the dam, there's nowhere for it to go. It just builds up. That buildup doesn't just reduce capacity, it shifts water pressure onto different parts of the dam and alters how water flows through its turbines and spillways. The result is a system that's constantly adjusting to an ever-changing internal load, and that kind of pressure over time wears things down. Then you got aging materials. The main dam was structurally completed in 2006, but that doesn't mean it was left alone. In fact, the full power station only became fully operational in 2012. And the final part of the project, a massive ship lift, wasn't finished until 2015. That means different parts of the structure were completed at different times, and they've been weathering the elements for over a decade now. Concrete expands and contracts with heat and cold. Steel corrodes, seals degrade. It all adds up over time. Engineers inspect and maintain the dam constantly, but some experts have raised concerns that early construction might not have met the highest standards. Hydrologist Wang Weilo, one of the loudest voices of criticism, has even claimed there were signs of cracking during construction and possible issues with concrete quality. These claims haven't been confirmed by the government, but they add to the worry that not everything behind the scenes is rock solid. One of the more delicate balancing acts the dam has to manage is between energy generation and flood control. When the reservoir is full, the dam can generate its maximum output of electricity. But in flood season, the water level has to be lowered ahead of time to create space for incoming rain. That trade-off creates a constant back and forth between power production and safety. If heavy rains come sooner or harder than expected, the operators might not have enough time to lower the reservoir, and that could raise the risk of overtopping, where water spills uncontrollably over the top of the dam. Even though the dam is equipped with emergency spillways, a sudden surge, say from a failed upstream dam or a monster storm, could overwhelm the system. And extreme weather isn't just a possibility anymore. Climate change is pushing rainfall patterns into new territory. The summer of 2020 saw record-breaking floods in China, pushing the Three Gorges Dam to its limits. The water level rose to over 165 meters, very close to its designed maximum of 175 meters. In response, authorities opened floodgates, unleashing flows of more than 70,000 cubic meters per second to try and lower the pressure. But with each flood season, the margin for error seems to shrink. And this year, June of 2025, weather forecasts are predicting another season of intense rainfall. Engineers are already working to lower the reservoir, but no one knows if that will be enough. So, when you put it all together, earthquakes, landslides, sedimentation, aging infrastructure, and increasingly extreme weather, you can start to see how a chain reaction might begin. The dam doesn't have to fail in one big moment. It could be a slow buildup of smaller issues, stacking up until something finally gives, and if it does, the next part of the story begins. What happens when a wall of water starts racing toward some of the most populated cities on Earth? That's what we'll explore next. If the Three Gorges Dam were to collapse, the destruction would be unlike anything China or the world has ever seen. This isn't just a local disaster. This would be a chain reaction of flooding, infrastructure failure, and mass displacement on an unimaginable scale. To understand how devastating it could be, we have to follow the water step by step, city by city, hour by hour. The first to be hit would be Yicheng, the city closest to the dam. Yicheng sits less than 40 kilometers downstream. Within minutes, a wall of water tens of meters high could crash into its streets, wiping out homes, power lines, and transportation routes. Most residents would have little or no time to escape. Bridges would collapse. Roads would vanish under waves of debris-filled water. The force of that initial surge could be enough to destroy every structure in its path. But the water wouldn't stop at Yicheng. It would keep moving downstream, building momentum as it rushed through the Yangtze River basin. Within hours, the flood could reach Jingzhou, a historic city with a population of over 5 million people. Much of Jingzhou lies on flat land near the river. That geography means slower drainage and deeper flooding. Even if early warnings were issued, evacuation would be chaotic, transportation would be overwhelmed, and low-lying neighborhoods could be completely submerged. Next, the water would bear down on Wuhan. This is not just a large city, it's a mega-city. Over 11 million people live in Wuhan, and it's a key hub for finance, transportation, and technology. 3 major rivers, including the Yangtze and Han, converge there. If floodwaters from upstream hit Wuhan at the same time as heavy local rainfall, the result would be catastrophic. Subways would flood, the airport would be rendered useless, power stations, water treatment facilities, and hospitals could all be knocked offline. Rescue efforts would be nearly impossible in the early hours, and tens of thousands of lives could be at risk. The damage would continue far beyond Wuhan. Cities like Zhejiang, Nanjing, and even Shanghai, over 1,000 kilometers away, could feel the effects. While the force of the water would weaken over that distance, the volume would remain staggering. In lower areas, floodwaters could spread across vast swaths of farmland, drowning crops and displacing rural communities. Ports and industrial zones along the Yangtze River would be paralyzed. Highways and railway lines would be washed out. The cost to China's economy alone could stretch into the trillions of dollars. One of the most devastating long-term effects would be the collapse of the interconnected dam and levee systems along the Yangtze River. The Three Gorges Dam is part of a larger network of over 100,000 dams across the country, many of which are smaller and older. If the Three Gorges Dam failed, the flood would likely breach several of these structures as it surged downstream. Each failed dam would release more water, compounding the disaster and spreading it wider. Entire provinces could see their water systems permanently altered. And then there's the human cost. Conservative estimates suggest that over 400 million people live within the greater Yangtze River basin. Even if only a fraction of those people were directly affected, we're still talking about tens of millions displaced. Millions more could face shortages of clean water, food, and shelter. Disease outbreaks, especially in overcrowded evacuation centers, would be a serious risk. With supply chains cut and medical infrastructure damaged, emergency response teams would struggle to keep up. It would take weeks, possibly months, for aid to reach all the areas in need. Environmental damage would be another hidden but massive problem. The reservoir behind the Three Gorges Dam contains not only water, but also industrial runoff, sewage, and heavy metals that have settled there over years. If the dam failed, all of that would be swept downstream. Toxic materials could contaminate farmland, rivers, and coastal waters. The Yangtze River Delta, one of China's most fertile and economically vital regions, could be poisoned for years to come. In global terms, the collapse of the Three Gorges Dam would also disrupt international trade. Ports like Shanghai and Ningbo handle a significant percentage of China's exports. If those ports were flooded or cut off from rail and road transport, it would affect supply chains around the world, factories would shut down, prices for electronics, clothing, machinery, and other goods would spike globally. The economic ripple effect would be felt in Europe, North America, Southeast Asia, and beyond. But beyond all the statistics and projections, the heart of the tragedy would be the human stories. Families separated, entire neighborhoods erased, generations of history drowned in minutes. In many ways, the Three Gorges Dam was built to protect people from exactly this kind of nightmare. But if it were to fail, it wouldn't just be a collapse of concrete, it would be a collapse of trust, of planning, and of an entire way of life for millions. In the next part, we'll explore how prepared China is for such a worst-case scenario, and whether the systems in place today would be enough to stop the unthinkable from becoming reality. When it comes to the potential collapse of the Three Gorges Dam, the Chinese government has not been silent. There are emergency plans in place, but whether they are enough is another question entirely. A structure as massive and consequential as this demands a coordinated and layered defense system. Yet even with decades of planning, some cracks cannot be patched with paperwork alone. First, it's important to understand what kind of monitoring and early warning systems are already active. The Three Gorges Dam is equipped with thousands of sensors that measure pressure, stress, water levels, and seismic activity. These sensors transmit real-time data to control centers in Yichang and Beijing. Engineers claim that the dam can withstand earthquakes up to magnitude 7 and has overflow spillways designed to reduce pressure during extreme flooding. But no amount of data can offer total certainty. If the dam fails suddenly due to sabotage, a landslide, or a rare upstream earthquake, these systems would only provide seconds or minutes of warning to those in the path of destruction. Beyond the dam itself, China has developed a tiered emergency response structure. This includes local, provincial, and national crisis management teams. In theory, evacuation plans are regularly reviewed and practiced in some downstream cities. Large urban centers like Wuhan and Nanjing have contingency plans that include siren alerts, emergency broadcasts, and designated evacuation routes. Drones, satellite imaging, and even artificial intelligence tools are being used to track weather patterns and detect potential structural anomalies, but planning does not always translate into execution. One of the main challenges is geography. The areas most at risk lie along the Yangtze River, one of the most densely populated river basins on Earth. Some villages and towns are isolated or surrounded by mountains, with only narrow roads in and out. In such places, evacuation efforts could be delayed by traffic, poor communication, or landslides triggered by heavy rain. In larger cities, roads are often congested even during normal times. A mass evacuation of millions within a few hours is nearly impossible. There is also the question of political control. The Chinese government tightly manages public information. In the past, warnings about structural issues with dams or floods have been delayed, downplayed, or withheld altogether to avoid public panic. During the 2021 floods in Zhengzhou, for example, official reports did not fully capture the severity of the disaster until after the worst damage had occurred. If a similar pattern of secrecy happened during a Three Gorges emergency, valuable time could be lost, time that could save lives. In addition, while the Three Gorges Dam is the largest hydroelectric project in the world, China has over 98,000 other dams, many of them smaller, older, and more vulnerable. These dams form a cascading system of water control. If the Three Gorges Dam were to fail, that would place immense pressure on this entire system. The failure of even a handful of secondary dams downstream could make the disaster significantly worse, and unlike the main structure, many of these smaller dams are not as well monitored or maintained. On top of all this, military assets would likely be mobilized in the event of a collapse. The People's Liberation Army has rapid response units trained for flood rescue and logistics. Boats, helicopters, and temporary shelters could be deployed to major cities and evacuation zones, but again, scale is the issue. It is one thing to rescue thousands, it is another to respond to tens of millions needing aid all at once. If supply chains are broken, bridges washed away, and power grids offline, even the best equipped teams will struggle. China has made some efforts to improve community-level preparedness in schools and factories. Some citizens undergo annual emergency drills. Government apps can push evacuation alerts directly to smartphones. Civil defense shelters have been converted in some regions to handle flood refugees, yet access to these resources is uneven. Many rural areas still lack digital infrastructure or reliable emergency communication. International cooperation is also limited. Due to political tensions and national security concerns, the Chinese government does not openly share structural data on the Three Gorges Dam with other nations. This makes outside assessment difficult and hinders offers of international assistance. If the dam were to fail, countries downstream, especially those reliant on Chinese supply chains, would receive little advance notice or coordination. One key blind spot in China's emergency planning is environmental fallout. While the focus has largely been on water and human evacuation, there is less clarity on how the government would contain chemical spills or manage water-borne diseases in flooded areas. Large-scale flooding often causes sewage overflow, industrial leakage, and hazardous contamination. In the chaos of mass displacement, it is unlikely that environmental mitigation would be prioritized. In short, China has systems in place to monitor, respond to, and possibly manage a dam-related emergency, but none of them have ever been tested at the scale of a complete Three Gorges failure. Even with the most advanced technology, fastest troops, and strictest planning, the sheer size of the population and the speed at which such a disaster would unfold leave a terrifying question. Would any of it be enough? In the final part, we will examine the long-term consequences of a collapse, not just for China, but for the world. From food security and energy disruption to political fallout and global markets, the failure of this dam would echo far beyond the riverbanks. If the Three Gorges Dam collapsed, the devastation would not stop at China's borders. What begins as a physical disaster could rapidly spiral into an economic, environmental, and geopolitical crisis on a global scale. In this final part, we look beyond the immediate flood zones to explore how the world might feel the shockwaves of a failure that would alter global systems overnight. To begin, China plays a central role in the global economy. It is the world's largest manufacturing hub and the largest exporter of goods. The Yangtze River Basin is home to more than 400 million people and contributes more than 40% of the country's GDP. Major industrial cities like Wuhan, Chongqing, and Nanjing rely heavily on the transportation, water, and power infrastructure connected to the dam. If that infrastructure is destroyed, it would trigger an immediate collapse in manufacturing output, especially in electronics, automotive parts, and heavy machinery. The supply chain disruption would be massive. Ports and railways in the region would be paralyzed. Global companies that depend on Chinese factories, ranging from consumer tech brands to pharmaceutical giants, would experience immediate shortages. Products could disappear from shelves around the world within weeks. Shipping delays would skyrocket. Prices on raw materials and finished goods would spike, contributing to inflation in already fragile global markets. The energy impact would also be severe. The Three Gorges Dam is the single largest hydroelectric power station in the world. If it fails, its massive contribution to China's grid, around 2% of national energy, would vanish. While this percentage may sound small, it supports critical infrastructure in eastern and central China, including power for hospitals, water treatment plants, and communication systems. Rolling blackouts could follow across several provinces, straining emergency response and industrial recovery. Environmental consequences would not be limited to floodwaters. The Yangtze is a vital artery for agriculture and ecology. Its basin supports rice, wheat, and fish production for hundreds of millions. A sudden collapse would destroy crops, spread industrial toxins from submerged factories, and kill off entire aquatic ecosystems. This could lead to long-term food shortages within China and affect global food trade, particularly in Asia and Africa, where Chinese agricultural exports are critical. International financial markets would react instantly. Investors often respond to disasters with panic, and a collapse of this scale would send shockwaves through stock exchanges in Hong Kong, Tokyo, London, and New York. China's currency could fall, foreign investment could stall, and insurance firms with exposure to Chinese assets would face massive payouts. The economic ripple effect would likely trigger recessions in multiple countries, especially those closely tied to China through trade or debt. Then there's the political dimension. A collapse of the Three Gorges Dam would be seen not just as a natural disaster, but as a national failure. It is one of China's proudest infrastructure achievements, a symbol of power, progress, and engineering superiority. If it failed, the Chinese Communist Party could face intense public backlash. Protests could break out, especially if the government was seen as hiding information or mishandling the response. In the worst-case scenario, such a collapse could threaten internal political stability. Internationally, tensions could rise. Neighboring countries downriver, such as Vietnam, might demand answers or compensation if they are affected by flooding or water shortages. Some nations may accuse China of negligence or failing to maintain a project with global consequences. At the same time, geopolitical rivals might exploit the chaos to gain influence or negotiate more favorable trade terms. Cyber attacks, misinformation campaigns, and border tensions could all increase as a result. Humanitarian aid would become another flashpoint. If China requested or accepted international assistance, questions would arise about coordination, transparency, and access. Foreign governments and NGOs may be hesitant or restricted in what they are allowed to do. The sheer number of displaced people, possibly tens of millions, would overwhelm aid systems, and China might be forced to prioritize urban recovery over rural survival. This would raise serious ethical concerns and could strain relations with other countries already dealing with global refugee crises. In the long term, the collapse would permanently reshape how nations view megaprojects and large-scale dams. For decades, the Three Gorges Dam has been cited as an example of engineering ambition. Its failure could chill future hydroelectric investment, trigger stricter international engineering codes, and increase skepticism of top-down infrastructure development. At the same time, countries may double down on decentralizing power grids and water management systems to avoid similar catastrophes. Ultimately, the failure of the Three Gorges Dam would be more than a Chinese disaster. It would be a global turning point. From the floodplains of central China to the trading floors of distant financial capitals, every corner of the world would feel its impact. Whether through broken supply chains, rising prices, shifting alliances, or the haunting image of a drowned megastructure, the collapse would mark the end of one era and the start of something far less stable. Imagine waking up one morning to a news alert that the ozone layer, Earth's invisible shield high above us, was completely gone. Not damaged, not thinning, just gone. No warning. No time to prepare. The moment that happens, the entire planet would be exposed to levels of ultraviolet radiation that no living thing is built to handle. What used to be a layer of protection between us and the sun would suddenly become empty space. And from that moment forward, every second spent under the open sky would be dangerous. The ozone layer sits in the stratosphere and absorbs most of the sun's harmful ultraviolet B radiation. Without it, this intense UV radiation would flood the surface of the planet, especially in the daytime and in places closer to the equator. Within the first hour of exposure, people outdoors without protection would start suffering severe sunburns. Within a day, even short periods outside would lead to serious skin damage and raise the risk of skin cancer dramatically. Eyes would be at high risk too, with cataracts and blindness becoming a serious concern even with limited exposure. People would have to stay inside buildings with UV blocking windows or wear full body protection, including face shields, just to walk around during daylight hours. And it wouldn't just affect humans. Animals would suffer too. Livestock exposed to direct sunlight would get burned, and birds and other animals that live outside wouldn't survive long without shelter. Crops like corn, wheat, and soybeans, which feed millions, would begin to die off fast from overexposure to UV light. Plants don't have sunscreen. If this happened during the growing season, entire harvests would be lost. And we're not just talking about farming in one part of the world, this would happen everywhere. From the plains of Kansas to the rice fields of Southeast Asia, the damage would be immediate. Even in the oceans, things would start to break down. The top layer of the ocean, where tiny organisms called phytoplankton live, would take a huge hit. These organisms are the base of the marine food chain and are incredibly sensitive to ultraviolet radiation. If they began to die off, fish and other marine life would start disappearing too. All of this would start happening in just the first few days after the ozone layer vanished. This isn't something that would slowly creep in. The impact would be fast, brutal, and hard to stop. And this is just the beginning. In the next part, we'll look at what happens once the damage starts spreading across cities and countries, and how life on Earth would begin to shift in a matter of days. Within the first week of the ozone layer disappearing, entire cities across the globe would begin to change, not just in how they look, but in how people live. Streets would empty out during the day, schools and offices would close or shift to operating only at night. Outdoor construction projects, farming, sports, and even simple errands like going to the grocery store would become extremely dangerous without full-body UV shielding. Hospitals would be flooded with patients suffering from burns, eye damage, and heat exhaustion. Emergency services wouldn't be able to keep up. Cities like Phoenix, Dallas, and Los Angeles, places already used to hot sun, would be hit hard, but even northern cities like Minneapolis, Toronto, and Berlin wouldn't be spared. This wouldn't be a regional issue. It would be a global crisis. People living in rural areas, especially farmers, would be among the first to feel the impact on food. Within a matter of days, crops would begin to wither and die. The sunlight they need to grow would now be overpowered by ultraviolet rays that fry their leaves and damage their DNA. Entire harvests of corn, soybeans, wheat, lettuce, and fruit trees would be ruined. Greenhouses would become essential, but they wouldn't be able to keep up with the massive demand. In countries like India, China, the United States, and Brazil, food shortages would start to build up fast. And since this problem affects the entire planet at once, there would be no country left to rely on for imports. By the 5th or 6th day, military and government agencies would likely take over essential services in many areas. Public service announcements would run non-stop, urging people to stay indoors during the day and ration food and water. Outdoor areas would be covered in tarps or reflective UV-resistant materials. Solar panels, now overloaded by intense sunlight, could short out or become damaged from the heat and radiation. Power grids already stretched thin in summer months could start failing from the demand of increased air conditioning and emergency power use. Massive blackouts would become more frequent, especially in poorer regions that don't have strong infrastructure. Without power, staying indoors becomes more dangerous, especially in heat waves. Meanwhile, the oceans would begin to shift in a silent but deadly way. Coral reefs in the tropics would start bleaching almost immediately, dying off from radiation stress. Fish populations would decline fast, not just from the death of plankton, but from rising water temperatures and changing currents. Coastal fishing towns in Southeast Asia, the Caribbean, and parts of Africa would feel the loss in just a few days. For millions who rely on daily catches to eat, it would be a sudden and terrifying change. Ocean ecosystems would begin to unravel, setting off a chain reaction that scientists would have no way to stop. By the end of the first week, the planet would already be unrecognizable from what it was before. The skies would still look blue, but everything under them would be altered by the invisible radiation now flooding the surface of Earth. And next, things would only get worse. Next, we'll look at how the second wave of damage spreads, how entire ecosystems begin to break down, and what happens when Earth's most basic systems start collapsing. By the end of the second week, the disappearance of the ozone layer would begin triggering deeper, more permanent damage. Entire ecosystems on land and in the oceans would start to collapse. Forests, which normally absorb sunlight and carbon dioxide, would begin to wither. Trees in regions like the Amazon, the Congo Basin, and even the Pacific Northwest would show signs of leaf burn and cellular damage. Without the protective filter of the ozone layer, UV radiation would break down plant DNA at a cellular level. Trees would stop growing, leaves would fall too early, entire forests would go quiet as birds, insects, and mammals either fled or died off. It wouldn't be a slow change, it would be fast, chaotic, and unstoppable. Insects, which are vital to pollination, would vanish in huge numbers. Bees, butterflies, and beetles are highly sensitive to ultraviolet light. Without them, crops and wild plants that depend on pollination would stop reproducing. This includes food sources like apples, almonds, berries, and cucumbers. Within just a few weeks, the global food supply would shrink dramatically. Countries would start enforcing martial law around food production and transportation. What little food survived would be locked down and rationed. Grocery store shelves in major cities like New York, London, Tokyo, and Sao Paulo would be emptied within hours of delivery. As vegetation across continents died, dust and dry soil would take over once green fields. With less plant cover, winds would pick up dry particles and spread them into the air, causing massive dust storms in areas like the Great Plains, Central Australia, and parts of India and North Africa. These storms would not only make the air unbreathable, but would also carry toxins and radiation-baked materials into homes, cities, and water supplies. Respiratory illnesses like asthma and lung infections would rise quickly. Hospitals already overwhelmed from UV injuries would now have to treat people for breathing problems, infections, and starvation. The ice caps and glaciers, already under threat from climate change, would begin to melt even faster. The intense UV radiation would speed up melting across Greenland, Antarctica, and the Arctic. As fresh water poured into the oceans, sea levels would rise faster than ever before. Coastal cities like Miami, Dhaka, and Venice would face flooding within weeks. Combined with extreme heat, UV exposure, and food shortages, some areas would become entirely uninhabitable. Climate refugee numbers would explode. Millions of people would be forced to leave their homes with nowhere safe to go. Meanwhile, the animal kingdom would suffer massive extinctions. Amphibians, already fragile, would be some of the first to vanish. Frogs, salamanders, and toads depend on moist, shaded environments and are extremely vulnerable to radiation. Birds would stop migrating. Many would die in flight from UV damage to their eyes and feathers. Mammals would start to disappear too, not all at once, but in waves. Larger animals like deer, elephants, and bears would struggle to find shelter and food. Within 1 month, the planet would lose thousands of species. The natural world that people have known for thousands of years would begin to fade fast. And this isn't even the full picture. As we wrap up, we'll look at the long-term impacts on civilization itself. What happens when governments collapse, food systems shut down, and human survival is no longer guaranteed. By the second month, without the ozone layer, human society would be in full-scale crisis. Cities that once thrived with light, noise, and movement would fall silent. People would live mostly indoors, with windows blacked out and walls lined with reflective materials to keep the ultraviolet radiation out. Entire communities would become nocturnal, working and moving only at night, but even that wouldn't be safe forever. Food, water, and energy would run low. Communication networks would begin to fail. The internet, radio, and cell towers, overloaded by heat and power shortages, would go dark. Governments would declare states of emergency, but many would collapse under the pressure. In poorer nations, leadership would dissolve entirely as people fought to survive on their own. Nations with advanced technology might try to launch emergency space-based systems to shield parts of the planet. Massive mirrors in orbit or high-atmosphere aerosols could be tested to reflect sunlight. But these projects would take years to build, time the world no longer has. Temporary underground shelters would pop up across North America, Europe, and parts of Asia. Old Cold War bunkers would be reopened. Some people would flee to mountain caves or deep forests for protection. But most of the population, especially those in cities or low-income areas, would have nowhere to go. Death rates from radiation sickness, starvation, and heat stroke would rise fast. Global population would drop sharply within the first year. Mental health would begin to deteriorate on a wide scale. With no sunlight that's safe, people would suffer from severe vitamin D deficiency and depression. Children born during this period would face developmental problems from both radiation exposure and malnutrition. Medical supplies would run out, and doctors would be forced to choose who lives and who doesn't. Even clean drinking water would be hard to come by as radiation starts to contaminate surface lakes and streams. Boiling wouldn't help. Filters wouldn't be enough. Only deep sealed aquifers would remain safe for a while. Animals that had once adapted alongside humans, pets, livestock, even urban wildlife would die off or go feral. Streets that were once full of dogs and cats would become empty or dangerous. Zoos would shut down, unable to care for animals exposed to deadly light every day. Farms would collapse, even indoor ones, without reliable pollination and power. Some surviving communities might begin hunting again, relying on smaller underground species or stored meat. But it would not last long. By the 1-year mark, the Earth would be a different planet. The skies would still look blue, but the surface would be scorched, silent, and changed forever. Crops, forests, oceans, and wildlife would not recover easily. And humans would face the ultimate question: adapt underground in small, isolated groups or disappear completely. The economic toll by this point would be impossible to measure. Stock markets would have long since collapsed. Trade routes would no longer exist. Currency would be worthless in a world where food and water are all that matter. Nations would stop functioning the way we understand them. A return to tribal, survival-based communities would begin. History, science, art, and culture would be left behind, sacrificed in a desperate race to stay alive. This isn't just a worst-case scenario, it's a reminder of how fragile the balance of Earth really is. The ozone layer invisible and often forgotten, is one of the thin barriers that makes life on this planet possible. Without it, everything changes, and if we ever lost it completely, there would be no going back. Imagine stepping outside and feeling raindrops that sting your skin. The air smells sharp like burnt matches. Trees around you look sick. Their leaves are brittle, their bark is peeling, cars are corroding, their paint stripped away like they've been left out for years. Now imagine that this isn't a one-time freak storm, it's every time it rains. This is the terrifying world we would face if acid rain became the new normal. And the worst part? We could already be on that path. Acid rain doesn't mean rain that can melt your skin instantly, but it does mean rainfall that's mixed with dangerous pollutants like sulfur dioxide and nitrogen oxides. These gases are released into the air when fossil fuels are burned. From coal plants, car engines, and factories. They mix with water vapor in the sky and fall back to the ground as highly acidic rain. Right now, most countries have pollution laws in place to limit how much of this stuff gets released, but if those laws were removed, ignored, or just couldn't keep up anymore, acid rain wouldn't be rare, it would be constant. This wouldn't happen all at once. It would start slowly, probably in areas already dealing with heavy pollution. Think major cities like New Delhi, Beijing, or even Los Angeles. At first, people would notice changes in the environment, trees would begin to die, not just from the rain itself, but from soil losing its nutrients. Forests would thin out, rivers and lakes would become toxic to fish and wildlife, entire ecosystems would collapse. Within just a few years, places that were once green and alive would start to look gray and lifeless. Buildings would take a hit next. Acid rain eats away at stone, brick, and metal. Famous landmarks would begin to erode. Statues, bridges, and old buildings would crumble faster than anyone could repair them. Skyscrapers would rust and corrode. Infrastructure would start to break down in cities worldwide. What used to take decades of natural weathering could happen in just a few years, and people wouldn't be spared. While acid rain doesn't directly kill you when it falls, long-term exposure to the polluted air that causes it is deadly. Respiratory problems would skyrocket. Children and the elderly would be the first to suffer. Asthma, bronchitis, and lung disease would become far more common. Rainwater would no longer be safe to collect. Crops would fail, not just from toxic rain, but from poisoned soil. Food shortages would begin. This isn't a slow burn disaster. If acid rain became the new normal, it could flip the way we live upside down in just a few years. And once it begins, stopping it becomes harder and harder. In the next part, we'll look at how this new world begins to spread from cities to countryside, from farms to forests, and how different places across the planet would start to fall one by one. As acid rain becomes a regular part of life, the damage doesn't just stay in the cities where it started. It spreads outward, pushed by wind patterns and storm systems that carry pollution across borders and oceans. Within a few short years, this becomes a global disaster. Countries that thought they were safe, places with less industry or more environmental protections, start seeing the same signs. Trees that once formed dense green forests begin losing their leaves and bark. Lakes once teeming with fish become acidic pools. Mountain ranges, once home to diverse wildlife, turn into silent, barren landscapes. Agriculture is one of the first major systems to start falling apart. Acid rain changes the chemical makeup of soil. It strips away nutrients like calcium and magnesium, which crops need to grow. Even if farmers try to fertilize their land, the acidic rainfall keeps undoing their efforts. Wheat, rice, corn, and vegetables all begin to wither faster than they can be harvested. Livestock suffer too, drinking contaminated water and eating toxic grass. Within just 5 to 10 years, entire farming regions collapse. As rural areas begin to suffer, people flood into cities, hoping to escape the failing countryside. But cities aren't holding up either. Roads, power lines, water pipes, all of it is being worn down by constant exposure to corrosive rain. Concrete crumbles, metal rusts, blackouts become common, and clean water becomes harder to find. And because more people are now packed into these already failing cities, disease starts spreading fast. Polluted air weakens lungs. Contaminated water spreads illness, hospitals are overwhelmed. The systems people rely on to stay alive are collapsing. Countries start to panic. Governments try to act, but it's already too late to undo most of the damage. Emergency zones are set up, and mass evacuations are ordered in some regions, but there's nowhere left untouched. Remote islands, mountain villages, even deserts begin showing signs of acidic damage. Rainfall, once a symbol of life, now brings destruction. And it keeps falling, storm after storm. year after year. Cultural heritage is also under threat. Centuries-old temples, churches, and monuments are fading away. Famous sculptures dissolve in the rain, their fine details eaten away in months instead of centuries. Museums struggle to protect artifacts from the humid, acidic air. Generations of history are being erased right alongside forests and farmland. In this new world, the damage isn't just visible, it's deeply personal. The places people grew up in, the land they once depended on, the skies they once watched for hope, it's all turning against them. In the next part, we'll explore what life would look like across the globe as acid rain becomes a permanent part of the environment and how different regions respond to the crisis in their own desperate ways. As acid rain continues to dominate the skies year after year, the toll on the environment and human life grows even worse. Rivers and lakes, once sources of fresh water and food, become too acidic to support most fish and aquatic plants. Species start to disappear rapidly. Fish die-offs trigger a collapse in the food chain, affecting birds and mammals that depend on them. Wetlands, which act as natural filters and flood protectors, shrink and die off, leaving communities more vulnerable to flooding and drought. The forests, which once helped clean the air and regulate climate, weaken and vanish. Acid rain strips away the protective layers on leaves and needles, making trees vulnerable to disease, pests, and harsh weather. Entire ecosystems collapse as animals lose their homes and food sources. This rapid loss of biodiversity makes the planet less resilient to other stresses like climate change or new diseases. People's health also faces a steady decline. Constant exposure to polluted air and acid rain weakens immune systems and inflames respiratory systems. Cases of asthma, bronchitis, and other lung diseases soar. Drinking water contaminated by acid runoff leads to kidney and liver problems. Children and the elderly become especially vulnerable. Hospitals struggle to keep up with the rising wave of illness, while clean water and safe food become more scarce. Governments try different approaches to manage the crisis. Some build massive water treatment plants to clean the increasingly toxic water supplies. Others try to capture emissions more aggressively, but the damage already done means the environment can't bounce back quickly. The chemical changes in soil and water are long-lasting. Years of acid rain mean nutrients that plants and animals rely on are permanently washed away. Cities attempt to adapt too. They cover exposed surfaces with special coatings and plant acid-resistant greenery in urban parks. But these solutions are expensive and don't work everywhere. The economic strain grows as crops fail, infrastructure crumbles, and healthcare costs rise. Countries heavily dependent on farming and natural resources suffer the worst, while richer nations spend billions trying to hold the damage at bay. By this point, acid rain is no longer a rare or seasonal event. It's a harsh and constant reality for billions of people worldwide. The way humans live, work, and interact with the planet has changed forever. The full scale of the disaster is clear. The environment is collapsing and humanity is scrambling to survive in a world where the sky itself is a threat. In the final part, we will explore the long-term consequences and the potential paths forward, if there is any hope left to reverse or survive this devastating new normal. As acid rain becomes the new normal, the long-term effects reach far beyond what anyone could have imagined. Entire regions become nearly unlivable as soil turns toxic and crops fail year after year. Without healthy plants to anchor the ground, erosion accelerates, causing landslides and the loss of fertile land. Food shortages become widespread, leading to massive hunger and malnutrition. People are forced to leave their homes in search of safer places, triggering waves of migration and conflict over dwindling resources. The damage to infrastructure grows worse too. Bridges, roads, and buildings corrode rapidly under constant exposure to acidic water. Water pipes and electrical systems break down, leaving millions without clean water or power. Cities struggle to maintain basic services, and governments face the enormous challenge of rebuilding while still fighting the environmental crisis. These failures add to the daily hardship for people trying to survive in an increasingly hostile world. Human health crises worsen as toxic water and polluted air cause new diseases to spread. Hospitals are overwhelmed, and many places lose access to medicine and doctors. The stress on mental health also rises as communities face uncertainty, loss, and fear. Children grow up in a world where outdoor play is limited and clean water is a luxury. Despite the severity of the disaster, some efforts at recovery emerge. Scientists develop new technologies to neutralize acidic water and restore damaged soils, but these solutions require massive resources and time. International cooperation becomes crucial, as no single country can handle the crisis alone. Still, the scale of destruction makes full recovery seem almost impossible. The damage done over decades means the environment may never fully return to how it was. In this harsh new reality, humanity is forced to rethink how it interacts with the planet. Sustainable living and aggressive pollution control become more than just ideals. They are essential for survival. But the question remains, can we learn from this disaster before it is too late? The possibility that acid rain becomes the new normal serves as a powerful warning. It reminds us how fragile our planet is and how quickly human actions can tip the balance. The future depends on what choices we make today, whether we take care of the Earth or watch it slip away into a toxic, lifeless world. Just off the coast of Oregon, Washington, and British Columbia lies one of the most dangerous fault lines on Earth. Yet most people living nearby rarely think about it. It's called the Cascadia Subduction Zone, a massive geological boundary stretching more than 700 miles from Northern California to Vancouver Island. For over 3 centuries, this fault has remained locked in silence. But geologists know that silence doesn't mean safety. In fact, it's the exact opposite. This fault is storing energy, an unimaginable amount of it, and eventually that energy will be released in the form of a devastating earthquake. The last time Cascadia ruptured was on January 26th of the year 1700. That magnitude 9.0 event triggered a tsunami so powerful it crossed the Pacific and struck Japan with no warning. Today, more than 300 years later, the stress beneath the surface has returned, and according to scientists, it's only a matter of time before it strikes again. The question isn't if Cascadia will break, it's when, and when it does, the Pacific Northwest will be changed forever. In the parts that follow, we'll explore what exactly that timeline of destruction could look like, from the first 5 minutes to the months and years that follow. It begins without any warning. Deep beneath the cold waters of the Pacific Ocean, the Juan de Fuca plate suddenly slips beneath the North American plate. This massive rupture sets off a chain reaction that will unfold in real time, starting with the violent shaking of the Earth itself. The seismic waves burst outward at more than 3 miles per second, racing toward the densely populated coastlines of Northern California, Oregon, Washington, and British Columbia. The moment the shaking begins, everything changes. Along the coast, where the seismic energy hits first, the ground moves with a brutal rolling force. This isn't the kind of quick jolt you might expect from a small quake. It's a relentless, rumbling motion that lasts anywhere from 5 to 7 full minutes. That may not sound long, but in an earthquake, even 30 seconds can feel like an eternity. Structures not designed to withstand long-duration shaking, like older brick buildings and wooden homes, will start to come apart. Bridges will bend and crack. Landslides will roar down unstable slopes, wiping out anything in their paths. The landscape itself begins to shift. In some coastal zones, the ground may drop suddenly by as much as 6.5 feet. This is called subsidence, and it instantly increases the risk of flooding in areas that were already vulnerable. In inland cities like Portland, Seattle, and Vancouver, the tremors will still be severe, though not as violent as at the coast. Tall buildings will sway dangerously. Glass will shatter and fall from above. Electrical grids will short out, plunging entire regions into darkness. Cell towers and communications systems will fail almost immediately, cutting people off from help. In less than 5 minutes, the entire Pacific Northwest will be in chaos. Roads will be impassable. Power and water will be gone. For millions of people, daily life will cease in an instant, and the real disaster will only just be beginning. As the last waves of shaking fade, the threat intensifies. Beneath the Pacific, the sudden shift of the seafloor has displaced an enormous volume of water. That violent movement sends a tsunami racing outward in every direction. For those along the coast, the earthquake was the only warning they will get. There won't be time for official alerts or evacuations. In many areas, the water will arrive in as little as 15 minutes. This won't be a single wave. It will be a series of towering surges, some possibly reaching 100 feet in height. These waves will carry debris, splintered wood, metal, vehicles, and they'll move fast, flooding entire towns with astonishing force. Low-lying areas will be hit hardest. The ocean will push inland for miles, sweeping away everything in its path. Homes, schools, and hospitals will be gone in moments. Roads will vanish under water and wreckage. And then as the first wave recedes, another will follow. The flooding may continue for up to 12 hours. During that time, the coastline will be transformed. Emergency services won't be able to reach the disaster zones, and survivors will have no way to communicate or call for help. The towns that once dotted the shorelines of Washington and Oregon will be reduced to isolated ruins, cut off by both water and destruction. People who managed to escape the shaking will now be running for higher ground, many on foot, with no clear idea of how long the danger will last. Historical accounts from indigenous coastal communities describe similar events during the last Cascadia quake in the year 1700. Entire villages disappeared overnight. In 21st century towns, built closer to sea level and with larger populations, the impact will be even greater. These next 30 minutes will turn a devastating earthquake into a full-scale regional catastrophe, one that reshapes the coastline and leaves behind a humanitarian emergency of unimaginable scale. By the time the sun rises over the Pacific Northwest, the landscape will be nearly unrecognizable. The earthquake and tsunami will have left behind a trail of destruction stretching from northern California through Oregon and Washington and up into southern British Columbia. Coastal communities will be in ruins. Entire neighborhoods will be submerged or flattened, and survivors will be stranded with no power, no water, and no way to reach the outside world. Inland cities like Seattle, Portland, and Eugene will not have faced the full force of the tsunami, but they will be reeling from the earthquake. Infrastructure will be critically damaged, water systems will be compromised by countless ruptures in pipes. Gas lines will leak, sparking fires that burn uncontrolled as firefighters struggle with broken hydrants and impassable streets. Hospitals will be overwhelmed, running on backup generators if they are even still standing. Medical staff will be forced to treat injuries in parking lots or wherever open space is available. Transportation will be paralyzed, bridges along Interstate 5 and other major highways may be damaged or collapsed, isolating entire cities. Airports could be out of service, rail lines twisted, ports shut down, supply chains for food, medicine, and fuel will be cut off. Shelves will empty quickly. For millions of people, daily life will become a desperate search for clean water, food, and shelter. Emergency responders will be stretched thin, focusing first on the worst-hit coastal regions, if they can get there at all. With limited communication, coordination between state and federal agencies will be chaotic. Entire towns may go hours or even days without any outside contact. Neighborhoods will have to rely on themselves. This is when personal and community preparedness becomes critical. Those who followed the Be 2 Weeks Ready guidance will fare better. But for many, the full reality of the disaster will begin to set in. In just 24 hours, the region will have shifted from modern, connected cities and towns to a disconnected patchwork of survival zones, each one struggling to understand what happened and what might come next. As the days turn into weeks, the Pacific Northwest will be facing one of the longest and most difficult recovery efforts in modern history. What began in minutes with a rupture beneath the ocean will evolve into years of rebuilding homes, infrastructure, and lives. Search and rescue operations will continue, but progress will be slow and dangerous. Many communities, especially along the coast, will remain completely cut off for weeks. Supplies may need to be airlifted into isolated areas, and some survivors might not be reached for 10 days or more. Basic services like clean water, electricity, sanitation, and medical care will take months to restore in urban centers and much longer in rural or coastal areas. Engineers estimate that full utility restoration to all impacted regions could take up to 3 years. Roads and bridges will have to be rebuilt from the ground up. In some places, subsided land will no longer be livable, and entire neighborhoods may need to be relocated. The coastline itself will have permanently shifted, both physically and in the way it can be used. The economic consequences will be staggering. Businesses will be destroyed or closed indefinitely. Shipping through major ports like Seattle and Portland could halt entirely for weeks, damaging national and international supply chains. Agriculture, a key industry in the region, will suffer from both infrastructure damage and logistical breakdowns. Insurance claims will be massive, but not everyone will be covered. Federal aid will pour in, but even that may not be enough to rebuild what was lost. Psychologically, the toll will be just as heavy. Families will be separated, entire towns will mourn lost neighbors, schools may be closed for extended periods. For those who survive, the trauma of the event, especially for children, will linger. Communities will have to navigate not only rebuilding their homes, but rebuilding their sense of safety and normalcy, and yet recovery will come. Just like after other major disasters, the people of the region will begin to come together to restore what they can. Towns will rebuild stronger, awareness will grow. Preparedness will become part of the culture. But the legacy of the Cascadia earthquake will never be forgotten. It will stand as both a warning and a testament of how devastating nature can be and how essential it is to prepare before the ground begins to shake. Imagine a tornado so powerful that it shatters everything we know about storms. Right now, the strongest tornadoes we measure are rated as F5 on the Fujita scale, which tops out at wind speeds of around 265 miles per hour. But what if a tornado was even stronger, an F6? This kind of storm doesn't officially exist, but scientists have speculated about it because as technology and climate conditions change, extreme weather might become more intense. If an F6 tornado did hit the Midwest or NULRM, the area often called Tornado Alley, which includes states like Oklahoma, Kansas, Nebraska, and Missouri, the damage would be beyond anything ever recorded. Wind speeds in an F6 tornado would likely exceed 300 miles per hour. To put that in perspective, the strongest tornado on record, the El Reno tornado in 2013, had winds estimated at around 280 miles per hour. With wind speeds that extreme, the tornado would pick up entire buildings, tear apart roads, flip cars like toys, and uproot trees by the millions. The air pressure inside the tornado would be so low it could literally cause buildings to explode from the inside out. This kind of force would create a path of destruction miles wide and tens of miles long, wiping out everything in its path. Because the Midwest has many small towns and farms spread across vast open spaces, the tornado could hit rural areas hard, destroying homes, barns, power lines, and night crops. But it could also strike larger cities like Wichita, Kansas City, or Omaha, causing massive destruction on an urban scale. The tornado would likely move very fast, traveling at speeds of 50 to 70 miles per hour or more. That means the storm could tear through an area in just a few minutes, giving people very little time to react. Emergency sirens might sound, but with such little warning, many would struggle to find safe shelter in time. Even sturdy storm shelters might not survive the incredible winds of an F6, because tornadoes usually happen during spring and early summer in the Midwest, often in the late afternoon or early evening. Many people might be caught off guard while outside or driving. The combination of suddenness and sheer power would make an F6 tornado one of the deadliest natural disasters possible in the region. Over the next few videos, we'll explore what kinds of places would be hit, how the timeline of destruction might unfold, and what the aftermath could look like. But first, it's important to understand just how intense this storm could be and what would happen while it's raging through the heartland. If an F6 tornado tore through the Midwest, the number of towns, cities, and communities impacted would be staggering. Tornado Alley is home to millions of people spread across hundreds of cities and countless smaller towns and rural areas. Imagine a storm so massive that its path could be 5 miles wide and stretch for more than 50 miles in length. This kind of tornado wouldn't just touch down in one spot and disappear. It would carve a continuous trail of destruction across multiple states, leaving very few areas untouched. Major cities like Oklahoma City, Wichita, and Kansas City could be caught in the storm's path. These urban centers, with their dense populations and infrastructure, would face overwhelming damage. Skyscrapers and large buildings would likely be reduced to twisted steel and rubble. Neighborhoods would be flattened, leaving thousands without homes or shelter. Airports, hospitals, and schools might be heavily damaged or destroyed, severely limiting emergency response efforts. Even smaller towns and farming communities, which often have fewer resources to begin with, would be completely leveled. Roads and bridges could be swept away, making it nearly impossible for rescue teams to reach survivors quickly. The timeline of destruction would be terrifyingly fast. An F6 tornado traveling at 60 miles per hour would pass through a town in mere minutes, but the damage left behind would last for years. The storm would likely begin early in the afternoon, forming from a powerful supercell thunderstorm that rapidly intensifies. As the tornado touched down, people might see the sky darken with swirling debris and hear a terrifying roar louder than a jet engine. Within moments, the storm would unleash winds so strong they could tear the roofs off buildings and hurl cars through the air like toys. Power grids would fail across entire regions, plunging millions into darkness. Emergency services would be overwhelmed immediately as calls for help flood in from everywhere. In the hours after the tornado passed, chaos would set in. Roads blocked by fallen trees and debris would slow rescue and recovery efforts. Hospitals would be overwhelmed with injured people and temporary shelters would struggle to accommodate thousands left homeless. The full scale of the damage wouldn't be clear until daylight, but it would be obvious that the Midwest was facing one of the worst disasters in its history. The next parts will explore what comes after the storm, how communities cope, respond, and begin the long process of rebuilding. Once the F6 tornado is past, the Midwest would be left in a state of utter devastation. The damage wouldn't just be visible, it would be overwhelming. Entire neighborhoods would be wiped out, leaving only twisted metal, shattered glass, and splintered wood where homes once stood. Streets would be clogged with debris, fallen power lines, smashed vehicles, and uprooted trees blocking every path. Emergency services would face one of their greatest challenges ever as they race against time to find survivors amid the rubble. Hospitals, many damaged or destroyed by the storm itself, would be struggling to treat thousands of injured people. Temporary medical tents might be set up in parking lots or open fields, but the sheer number of casualties would quickly stretch resources thin. Communications would be unreliable because cell towers and landlines could be knocked out, making coordination difficult. First responders would be forced to rely on radios and satellite phones, but even then, the scale of the disaster might overwhelm the system. Search and rescue teams would work around the clock using trained dogs, drones, and thermal imaging to locate anyone trapped beneath debris. Many people would be displaced with nowhere to go. Emergency shelters and community centers, schools, and churches would quickly fill up, but the loss of homes and essential services would mean many families face weeks or even months of uncertainty. Food, water, and medical supplies would become scarce in some areas, forcing relief agencies to organize massive aid efforts. The weather could also be unpredictable in the days following the storm, with rain and storms making cleanup harder and raising the risk of disease in flooded or damaged areas. Power outages would stretch across multiple states, affecting millions. Without electricity, water treatment plants and fuel stations might shut down, making basic needs like clean water and gasoline hard to come by. Many people would rely on generators, but fuel shortages and unsafe usage could lead to further problems. In addition, the destruction of roads and highways would slow down aid delivery and slow the arrival of help from neighboring states and federal agencies. The immediate aftermath of an F6 tornado would be a terrifying, chaotic time, filled with danger, heartbreak, and uncertainty. Yet amid this chaos, communities would begin to pull together, helping neighbors and working to clear debris and rebuild. But the scale of this disaster means recovery would be a slow, difficult process that would test the resilience of the entire region. The final part will look at what the long-term recovery might involve, including the economic and social impacts that would ripple through the Midwest for years to come. The long-term effects of an F6 tornado hitting the Midwest would be nothing short of catastrophic. After the immediate rescue and relief efforts, the true scale of rebuilding would begin to sink in. Entire communities would need to be reconstructed from the ground up. Homes, schools, businesses, and critical infrastructure like power plants, water systems, and roads could take years to repair or replace. For many small towns, the damage might be so severe that rebuilding wouldn't just be difficult, it could be impossible without outside help. Some places might never fully recover, leading to permanent population loss and economic decline. The financial toll would be staggering. Insurance companies would face billions of dollars in claims, and the government would likely need to provide massive aid packages to support recovery. Businesses destroyed or severely damaged could close forever, leading to high unemployment in already vulnerable rural areas. Farms wiped out by the storm would disrupt food production, affecting local and national markets. With roads and railways damaged, supply chains would be interrupted, causing shortages and delays in everyday goods. The disruption to daily life would ripple across the country, showing how interconnected the Midwest is to the rest of the United States. Beyond the physical and economic damage, the social impact would be profound. Thousands of families would be displaced, many losing everything they own. Mental health challenges like anxiety, depression, and post-traumatic stress disorder would rise sharply as survivors cope with loss and uncertainty. Schools damaged or destroyed would leave children without a normal learning environment. For months or even years, communities would need to come together to support each other, but the scale of the disaster might stretch local resources to the breaking point. Still, the Midwest is known for its resilience. Over time, rebuilding efforts would bring hope, and new, stronger buildings might rise in place of the old. Disaster planning and emergency response systems would likely improve, driven by the lessons learned from such a devastating storm. However, the memory of an F6 tornado would linger for generations, a reminder of the power of nature and the importance of preparedness. This hypothetical disaster shows just how fragile life can be in Tornado Alley, and why understanding and respecting these storms is so important for everyone who calls the Midwest home. The asteroid slams into the Central Pacific with an energy release equivalent to roughly 60 million megatons of TNT. That is more than 1 million times greater than the largest nuclear weapon ever detonated. The Pacific Ocean, despite being miles deep, barely slows it down. The water instantly vaporizes into a colossal column of superheated steam, stretching dozens of miles into the atmosphere. In less than a second, both the asteroid and millions of tons of ocean are gone, transformed into energy, heat, and chaos. A crater does not form like it would on land. Instead, a temporary cavity miles deep opens in the sea, exposing the ocean floor and punching directly into the Earth's crust. That rupture triggers an earthquake so powerful it exceeds magnitude 12, an intensity no human structure is designed to survive. Surrounding tectonic plates tremble, sending pulses of seismic energy across the globe. As the ocean collapses back into the cavity, an enormous wall of water is ejected outward. The initial wave is more than 1 mile high, an unstable tower of sea surging away in every direction, and it's not just one wave, it is the birth of a tsunami complex so powerful it dwarfs anything recorded in human history. Simultaneously, shock waves explode outward through the air. These atmospheric pressure waves travel faster than the speed of sound, flattening everything in their path. Ships are shattered like toys, birds are instantly killed mid-flight. The winds they carry are stronger than any tornado ever recorded, and they hit hundreds of miles away within minutes. From above, a monstrous plume rises, superheated steam, rock vapor, and asteroid debris reaching the stratosphere. It does not simply drift, it spreads rapidly, carried by high-altitude winds, setting the stage for what is coming next, a planet-wide crisis. The impact is over in seconds, but the consequences are only beginning. With the asteroid gone and the Pacific still heaving from the blow, the devastation starts to spread outward in terrifying waves, both literal and atmospheric. The mega tsunami, born from the impact, a traveling mountain of water, is now surging across the globe. Though the wave lowers as it moves away from the point of impact, it still towers over coastlines thousands of miles away. Within just a few hours, it reaches the shores of North and South America, Southeast Asia, Australia, and island nations caught in the crossfire. Some waves still rise hundreds of feet high, swallowing harbors, cities, and entire regions in minutes. The ocean becomes a weapon, it tears through ports, sends freighters crashing into inland buildings, and turns cars, trees, and homes into projectiles. Coastal populations have little to no warning. Communications are down. Power grids have already begun to fail under the strain of the seismic shock, and satellites knocked off course during the impact are barely functioning. Aid is impossible. Roads are gone, airports are underwater, entire regions are cut off. But what follows from above might be even worse. The massive plume of material launched into the upper atmosphere during the impact has begun to fall back, but it has not come down gently. As billions of particles re-enter Earth's atmosphere, they ignite. What begins as a distant flicker becomes an all-sky rain of fire. Every continent sees it, tiny blazing specks, streaking downward in the thousands. The heat from these returning fragments doesn't just light up the night, it raises atmospheric temperatures so suddenly and violently that dry landscapes, grasslands, and even forests burst into flames before anything touches them. By the end of the first day, global fires rage across multiple continents. From the Amazon basin to Siberian forests, from Australian bushland to the grass plains of North America, the land itself begins to burn. Smoke columns reach into the stratosphere, mixing with volcanic ash from eruptions triggered earlier by the planetary shock. The air is turning black. Volcanoes, long dormant or merely rumbling, have been jolted awake. The energy from the asteroid impact destabilized pressure points in Earth's crust, setting off a chain reaction. Mounts like Indonesia's Tambora, Alaska's Redoubt, and the Pacific's own Ring of Fire begin erupting almost simultaneously. These aren't small eruptions, they are colossal, spewing sulfur dioxide, ash, and rock into skies already choked with soot. Each eruption further dims the sun and cools the planet, and in the oceans, shockwaves from the asteroid continue to echo. Underwater, landslides and tectonic disturbances create secondary tsunamis. Currents shift. Oceanic conveyor belts, which help regulate global climate, begin to falter. Ecosystems both above and below water are collapsing, fast. Coral reefs bleach instantly under the heat and sediment. Fisheries that once fed millions are obliterated. Within less than 24 hours, the world is barely recognizable. Fires rage, skies darken, and coasts have vanished. But this is only the beginning of a deeper crisis, one that will not just reshape cities and countries, but the entire global climate for years to come. By the time the fires die down and the last tsunamis fade, Earth is already entering a new phase, one far quieter but even more deadly. Without much sunlight getting through the thick cloud of soot, ash, and aerosols now circling the planet, global temperatures start to plummet. What was once a world of heat and chaos turns cold and dim. This is the beginning of what scientists call an impact winter. Within just a few weeks, crops around the world begin to fail. Farming regions that once produced enough food to feed millions are now covered in frost or drowning in darkness. In tropical zones where temperatures used to hover around 80 degrees Fahrenheit, the mercury struggles to reach 40. In temperate regions, snow falls in what should be summer, and in the northern and southern extremes, the cold is bone deep and endless. Rain no longer falls like it used to. Instead, acidic snow and freezing rains sweep across continents, carrying with them toxins pulled from the atmosphere. The chemicals released by the impact, like sulfur dioxide, carbon monoxide, and nitrates, fall back down to the surface, poisoning freshwater sources and damaging what little vegetation survives. Rivers turn brown, lakes develop oily films. Even groundwater becomes unsafe in many regions. With no functioning agriculture and wild ecosystems collapsing, mass starvation takes hold. Livestock perish in the cold, crops rot or never sprout. Supermarket shelves, if they still exist, are permanently empty. Food becomes a form of currency. Some countries with stored grain reserves last a little longer, but within a few months, most of the global food supply is gone. Cities become silent, not because of tsunamis or fires anymore, but because of hunger. The oceans don't fare any better. Without sunlight, phytoplankton, the base of the marine food chain, virtually disappears. Coral reefs are already dead from the initial shock, but now fish populations crash completely, ocean temperatures fall, entire ecosystems vanish beneath the waves, survivors are scattered in bunkers, in caves, in underground shelters, small pockets of humanity huddle together, trying to wait out the cold. Nations have fractured, governments have collapsed or gone dark, most forms of communication are lost, power grids are useless, fuel is scarce, the internet as we knew it is long gone. People begin relying on local knowledge, community survival tactics, and sometimes brutal decision-making. And still, the skies remain dim. The once familiar blue has been replaced by a permanent gray shroud. Stars can rarely be seen. The moon glows faintly through the haze. And the sun? It's more of a pale disk now, barely warming the surface, offering little light and no comfort. The global climate has completely shifted, wind patterns change, rainfall stops in some areas and floods others. What used to be fertile land becomes tundra. Regions once too dry for farming now receive too much acidic rain. Coastal areas that somehow survived the waves are now too cold or too contaminated to support life. Months stretch into the first year, and it becomes painfully clear this is not a temporary disaster. This is a planetary reset. The climate system is broken. The biosphere is unraveling. And for the survivors left beneath this altered sky, the question is no longer, how do we fix this, but how do we endure what comes next? Years pass. The thick veil of dust and ash begins to thin, slowly settling into oceans, forests, and ice caps. Bit by bit, sunlight starts piercing through the clouds again, but the world it returns to is unrecognizable. Landscapes have shifted, ecosystems have collapsed, and human civilization, once spread across every continent, has been reduced to scattered remnants. As temperatures begin to rise again, this time due to the buildup of greenhouse gases like water vapor and carbon dioxide, the planet enters a new phase. Some regions experience extreme heat, while others face relentless storms or permanent drought. The climate doesn't return to what it was, it transforms into something unstable and unpredictable. In the oceans, life is trying to restart. New microbial life forms begin to appear, feeding on chemicals released during the catastrophe. On land, plants adapted to low light and harsh, cold conditions start to reestablish themselves in small patches, but species diversity is a fraction of what it once was. For the few surviving humans, rebuilding is slow and uncertain. Knowledge has been preserved in some places, but resources are scarce. Cities are buried, power infrastructure is useless, and transportation is nearly impossible. Those who remain rely on old-world tools and ingenuity to grow food, filter water, and survive. Generations later, the event will be remembered not as a singular disaster, but as the boundary between two Earths, before and after. Just as the Chicxulub impact ended the age of dinosaurs, this asteroid has ended the age of global civilization. Earth continues, life returns, but nothing is the same. And above it all, the sky remains a haunting reminder, beautiful, vast, and always carrying the possibility that one day it could happen again. Earth's magnetic field isn't just a scientific curiosity, it's a crucial part of what makes life on this planet possible. Generated deep beneath our feet in the outer core, this protective force emerges from swirling molten iron and nickel nearly 2,000 miles below the surface. The constant motion of this superheated liquid metal generates electric currents, which in turn produce Earth's global magnetic field, a geodynamo that has been running for billions of years. This magnetic field creates what's known as the magnetosphere, an enormous teardrop-shaped shield that extends tens of thousands of miles into space. Its job? To deflect charged particles from the solar wind and cosmic rays that constantly bombard our planet. Without this magnetic shield, Earth's atmosphere would gradually be stripped away by solar radiation, much like what happened on Mars billions of years ago. In other words, Earth's magnetic field is not just invisible, it's indispensable. But lately, scientists have noticed some unusual behavior. The most visible sign of this turbulence is the dramatic movement of the magnetic North Pole. For centuries, the North Magnetic Pole drifted gently through the Canadian Arctic. Then in the late 20th century, its speed began to increase. By the mid-1990s, it was moving about 9 miles per year. But by the early 21st century, it had accelerated dramatically to speeds between 34 and 37 miles per year, a rate 4 times faster than previous averages. Though that speed has recently slowed to around 22 to 31 miles per year, the overall trend remains clear. It's headed rapidly towards Siberia. This movement isn't just a scientific footnote. It has forced international agencies to update critical navigation systems more frequently. The World Magnetic Model, which underpins everything from smartphone compasses to military navigation tools, required an unexpected update in December of 2024 due to the pole's erratic sprint. But pole movement isn't the only concern. Earth's magnetic field itself is weakening. Measurements taken since the early 19th century show a decrease of about 9 to 10% in the field's global strength. And when scientists dig deeper into the geological record, they find that this decline may be even more pronounced, potentially a 30% drop over the last 3,000 years. One especially alarming feature is the South Atlantic anomaly, a vast region stretching from South America to Southern Africa, where the magnetic field is significantly weaker. In this zone, satellites are exposed to increased levels of radiation and are more prone to malfunctions. The Hubble Space Telescope and other satellites often power down sensitive instruments when passing through it. This weakening is not uniform to us. It's patchy, complex, and hard to predict. The magnetic field's behavior isn't random. It's the result of shifting patterns in the fluid outer core. Scientists believe 2 large magnetic regions under Canada and Siberia are locked in a kind of subterranean tug of war, influencing the position and movement of the magnetic poles. Right now, Siberia's magnetic region appears to be winning, hence the rapid movement of the pole in that direction. While all of this may sound apocalyptic, it's worth noting that changes in the magnetic field are not new. Earth's magnetism is naturally dynamic. The problem is that we're now starting to detect large-scale changes over human timescales, not over millions of years, but over mere decades. And this opens the door to much deeper questions. What happens if the weakening continues? Could it signal an impending magnetic reversal? Could it affect our technology, our climate, or even our biology? That's where we'll head next. So now that we've broken down the weird behavior of Earth's magnetic field, let's talk about what's really on the line. Because while the idea of a magnetic field collapse might sound abstract, the impacts would be anything but. This isn't just a science fiction scenario. If the field continues to weaken or goes into a full reversal, the fallout could hit every layer of modern civilization, from satellites in orbit to ecosystems on the ground. Let's start in space. Satellites, which form the backbone of global communication, navigation, and surveillance, are extremely vulnerable to radiation. Earth's magnetic field acts like a protective dome, deflecting charged particles from the sun. Without it, or even with it weakened, those satellites are exposed to intense solar and cosmic radiation. This isn't theoretical. We already see it happening in a region called the South Atlantic Anomaly. In that part of the world, the magnetic field is so weak that satellites passing through it often experience memory glitches or suffer from electrical failures. Engineers have to program some satellite systems to shut down temporarily while passing through this zone to prevent damage. Now imagine that anomaly expanding globally. Without adequate shielding, satellites in low Earth orbit would degrade much faster. Global positioning systems, satellite phones, weather forecasting tools, and internet access through orbital networks like Starlink could all become unreliable or fail altogether. And these systems are no longer just conveniences. They run everything from international finance to emergency services and air traffic control. But the risks don't stop in orbit. Power grids on the ground are also in the danger zone. When geomagnetic storms interact with Earth's magnetic field, they can induce electrical currents in long conductors like power lines. Under normal conditions, the magnetic field buffers a lot of that energy, but if it weakens or if a reversal causes temporary disruptions in the field structure, the energy from solar storms can surge into power grids with little resistance. A striking example of this occurred in March of 1989, when a geomagnetic storm, triggered by a solar flare, caused the entire power grid in Quebec, Canada to collapse. In less than 2 minutes, 6 million people were plunged into darkness. That storm happened under normal magnetic field conditions. If the field were weaker, a similar event could cause continent-wide blackouts, destroying high-voltage transformers that would take months or even years to replace. The economic cost would be staggering, but the human impact, hospitals without power, food supply chains disrupted, no communications, could be far worse. And then there's the biological angle. The magnetic field helps protect living organisms from genetic damage caused by cosmic radiation. With less protection, life on Earth, including humans, would be exposed to higher doses of ionizing particles. Over time, this exposure could lead to increased cancer rates and greater risk of developmental mutations in both humans and wildlife. While our atmosphere would still provide some shielding, high-altitude regions and areas near the poles, where radiation already penetrates more easily, would be hit hardest. Some scientists believe that during past geomagnetic excursions or reversals, early humans adapted their behavior in response to these increased radiation levels. There's evidence that ancient humans began using caves more frequently, potentially as a form of shelter from solar activity. In modern times, however, we depend on technology and global systems far more than our prehistoric ancestors did, and those systems are far more fragile. Even animals would struggle. Many migratory species like whales, birds, sea turtles, and bees rely on the magnetic field to navigate. They sense magnetic lines almost like a compass to guide them across vast distances. If those lines become distorted, these species could become disoriented, lose their migration paths, or stop reproducing effectively. Entire ecosystems could destabilize, especially in the oceans, where magnetic navigation plays a critical role for both predators and prey. And while some impacts, like atmospheric erosion gusto, would take an incredibly long time to fully develop, they are not impossible. Scientists believe that Mars once had a magnetic field similar to Earth's, but after it disappeared billions of years ago, the solar wind began stripping away its atmosphere, turning it into the dry, lifeless world we see today. While Earth's gravity and remaining atmospheric pressure would slow that process here, a significantly weakened field over many thousands of years could open the door to long-term atmospheric loss, with consequences no one can fully predict. In short, the magnetic field isn't just a fascinating part of Earth's inner workings. It's a critical piece of the puzzle that makes life seem Kuro and civilization near possible. As it weakens and shifts, we're not just watching a natural process unfold. We're potentially witnessing the slow unraveling of protections we take for granted every day. So how do we know all of this is happening? How can scientists tell that Earth's magnetic field is weakening, or that it might reverse in the future? The answer lies in a mix of space-based monitoring, geological records, and some pretty remarkable physics. This part of the story is not about guessing. It's about hard data and long-term observation. The first tool scientists use is satellite data. Since the early 2000s, a number of satellites have been launched specifically to monitor the strength and structure of Earth's magnetic field. The most advanced of these is the European Space Agency's SWARM mission, launched in the year 2013. SWARM consists of 3 identical satellites, flying in formation around the planet. They continuously measure the magnetic signals coming from Earth's core, mantle, crust, oceans, and even the ionosphere and magnetosphere. These measurements are incredibly precise, allowing scientists to map how the field changes in both space and time. What they've found is consistent with earlier predictions. The field has been steadily weakening, especially in a large region stretching from South America to Southern Africa, known as the South Atlantic Anomaly. In just the past 200 years, the global magnetic field has weakened by roughly 10%. But within the anomaly, the weakening has been far more rapid. This real-time monitoring is only part of the picture. To understand what might happen next, scientists also look backward, deep into Earth's geological past. They do this by studying volcanic rocks, ocean floor sediments, and even ancient clay pots. When molten lava cools, or when sediments settle, tiny magnetic particles inside them align with Earth's magnetic field at that moment. Once locked in place, those particles become permanent records of the planet's magnetic orientation and strength. These fossil magnets can be dated using radiometric techniques. Over the past several decades, this kind of research has revealed that Earth's magnetic field has reversed many times in its history. On average, it flips about once every 200 to 300,000 years. The last full reversal, known as the Brunhes-Matuyama reversal, happened roughly 780,000 years ago. That means we are long overdue by historical standards, though the field does not flip on a schedule. And what's even more interesting is that magnetic reversals don't happen overnight. Evidence shows they can take anywhere from 1,000 to 10,000 years to complete. During this time, the field becomes disorganized and weakens significantly. Magnetic north and south can wander unpredictably or even appear in multiple places at once. And that's exactly what's concerning scientists now. Magnetic north has been shifting at an accelerated rate since the early 20th century. It used to move around 10 kilometers per year. Now it's racing across the Arctic at nearly 50 kilometers per year. This movement has forced regular updates to navigation systems, including the World Magnetic Model used by everything from smartphones to military aircraft. At the same time, complex computer models of Earth's core, powered by supercomputers and guided by satellite data, are showing signs of increasing turbulence in the outer core, where the magnetic field is generated. This turbulence doesn't guarantee a reversal, but it aligns with what we would expect to see in the lead-up to one. Some scientists believe we may already be entering the early stages of magnetic excursion, a short-term disruption where the field weakens and shifts significantly without a full reversal. To be clear, there is still debate within the scientific community. Some researchers argue that we are simply seeing a natural fluctuation and that the field could stabilize again. Others warn that the current trend fits the pattern of past reversals and should be taken seriously, but no one is ignoring it. In fact, global magnetic monitoring has become a top priority for organizations like NASA, the European Space Agency, and geological institutes around the world. These groups are constantly updating models and issuing data to industries that rely on accurate magnetic positioning. So while we don't know exactly when or if a full reversal will happen, we're watching closely. The warning signs are real, the data is solid, and the consequences, as we've already seen, could be massive. What comes next might not be a sudden flip, but a long, messy period of change, and we may already be in the middle of it. If Earth's magnetic field suddenly vanished or flipped completely, life would not end. But the modern world as we know it would face serious challenges. This isn't about fireballs or earthquakes. The danger lies in something invisible but powerful, radiation from space. Earth's magnetic field acts as a giant shield, protecting us from solar winds and cosmic rays. Without it, that radiation would have a much easier time reaching the surface. One of the first and most immediate effects would be in the upper atmosphere. The magnetic field currently helps trap charged particles in radiation belts high above Earth, keeping them away from the surface. If the field weakened significantly, the solar wind could strip away parts of the atmosphere, especially the outer layers that contain ionized gases. While this would take time, it could increase our exposure to ultraviolet and high-energy radiation. The threat is even more immediate for satellites and spacecraft. Without a strong magnetic field, satellites in low Earth orbit would be far more vulnerable to damage from solar storms, Communication systems, GPS navigation, weather tracking, and military surveillance all depend on those satellites. A strong geomagnetic storm, similar to the one that hit Earth in the year 1859, known as the Carrington event, could fry entire networks and cause global blackouts. That event happened under normal magnetic conditions. Imagine the damage during a field reversal or collapse. Astronauts would be at greater risk as well. The International Space Station is still within Earth's protective field, but during a weakened period, that protection would shrink. Without additional shielding, astronauts could be exposed to harmful levels of radiation. Space agencies would have to delay missions or invest heavily in radiation-hardened technologies. On the ground, power grids would also be at risk. Changes in the magnetic field can induce electric currents in long conductors like transmission lines and pipelines. During past geomagnetic storms, some power systems experienced voltage irregularities, transformer failures, and blackouts. In 1989, a geomagnetic storm knocked out power in Quebec, affecting millions of people. That was a relatively minor event. A weakened or chaotic magnetic field would make these disruptions more frequent and severe. Migratory animals would face confusion too. Many species, such as birds, whales, and sea turtles, rely on Earth's magnetic field to navigate long distances. Studies have shown that some animals have magnetoreceptors in their brains or beaks that allow them to sense magnetic fields. A sudden change or reversal could throw off migration patterns, disrupt breeding seasons, and even cause population declines. Air travel could also be impacted. Polar flight routes, which pass through areas where the magnetic field is already weaker, would be more dangerous during solar storms. Airlines might have to reroute flights to avoid increased radiation exposure to passengers and crew, which would lead to longer travel times and higher fuel costs. And then there's human health. While Earth's atmosphere still offers protection from most radiation, a weaker field would let more high-energy particles reach the surface. Over time, this could slightly increase rates of cancer or genetic mutations, especially in people living at higher altitudes or closer to the poles. While the risk wouldn't be catastrophic, it's something scientists are actively studying. One lesser-known issue involves the technology that depends on magnetic orientation. Everything from smartphones to drilling equipment to submarines relies on magnetic data. During a field reversal, magnetic north would shift unpredictably. Compasses could become unreliable, and navigation systems that depend on magnetic input would need constant recalibration. This would affect shipping, military operations, and even underground mapping. Importantly, the effects of a full reversal wouldn't happen overnight. The transition could take hundreds or even thousands of years. During that time, the magnetic field would likely weaken, fluctuate, and form multiple poles before finally stabilizing. But this slow process doesn't mean the impacts would be easy to manage. Our infrastructure, communication networks, and global navigation systems were all built during a period of magnetic stability. We have no precedent for how to operate in a world where the field is shifting rapidly beneath our feet. In short, a magnetic collapse or reversal wouldn't destroy life, but it would challenge nearly every system our modern world depends on, from power and communication to transportation and navigation. While Earth has survived many reversals in the past, the stakes are higher now than ever before. The question isn't whether the planet can endure it. The question is, are we ready for it? If Earth's magnetic field reversed or significantly weakened, survival would depend not only on nature, but also on how well humanity prepares in advance. While we can't stop a geomagnetic reversal from happening, we can take real, concrete steps to reduce the impact on our technology, infrastructure, and health. First, let's look at forecasting. Scientists are already tracking changes in the magnetic field with high precision. The South Atlantic anomaly, a region where the field is particularly weak, has been growing and shifting westward. This anomaly poses increased risk to satellites and has drawn attention to the field's ongoing instability. With data from satellites like ESA's Swarm constellation and NASA's magnetospheric multi-scale mission, researchers can monitor these trends and spot signs of an impending shift. However, predicting exactly when a reversal might occur is still difficult. Earth's magnetic field is generated by the movement of molten iron in the outer core, and this geodynamo is complex and unpredictable. Some reversals in the past have taken as little as 1,000 years, while others took more than 10,000. There have also been failed reversals, where the field started to flip, but returned to its original state. This variability makes it hard to forecast the exact timeline or intensity of a future event. That said, there are steps we can take now to strengthen our resilience. One of the most critical areas is satellite design. Engineers are already working on developing satellites with stronger shielding against solar radiation. Space agencies are also exploring ways to reroute or power down satellites during major solar events to reduce damage. Having backup systems and redundancy in satellite networks would also help maintain communication and navigation during disruptions. On Earth, energy companies are beginning to study how geomagnetic storms interact with the power grid. Some are installing sensors and early warning systems to detect sudden spikes in ground currents caused by magnetic changes. Transformers and high-voltage systems can be built with protections that allow them to shut down safely instead of burning out. In areas like northern Canada or Scandinavia, where the field is naturally weaker, these protections could be especially valuable. Airlines may also need to rethink flight paths. During periods of high solar activity, polar flights could be redirected to lower latitudes to protect passengers and crew from increased radiation exposure. This has already been done during intense solar events in the past, and similar protocols would likely become more routine during a magnetic reversal. In the field of public health, medical researchers are beginning to study the long-term effects of increased radiation exposure. While Earth's atmosphere will still shield us from most of the sun's harmful rays, the added risk may lead to updated guidelines for radiation limits, especially for pilots, astronauts, and people living at high altitudes. Portable radiation sensors and protective materials could become more common in certain professions. Even navigation systems, both civilian and military, would require major adjustments. Modern aircraft, submarines, and shipping vessels often use magnetic compasses as backups to GPS systems. A magnetic reversal would force designers to rethink those systems or rely more heavily on non-magnetic alternatives. Military planners would also need to recalibrate long-range missile systems and battlefield navigation tools that use magnetic orientation. Education and public awareness could play an important role too. A magnetic reversal would not be a global catastrophe, but it could cause widespread confusion. Accurate, science-based communication would be essential to keep the public informed about risks and necessary precautions. Governments could release guidelines on how to respond to power outages, satellite failures, or navigation issues caused by a weakened field. In the longer term, some scientists have even proposed large-scale, space-based magnetic shields, giant structures that could help block radiation at key points between the Earth and the Sun. These ideas are still theoretical, but they reflect how seriously researchers are taking the potential risks of a magnetic collapse. Ultimately, while a full magnetic reversal would bring serious challenges, it would not be the end of the world. Life has survived dozens of magnetic flips over the past hundreds of millions of years. The difference now is that human society is built on fragile technology. Our survival won't depend on nature, it will depend on how seriously we take the warnings and how wisely we prepare for what's coming. A magnetic field reversal may be slow, silent, and invisible, but its consequences could be global. The best way forward is not fear, but readiness.